Hello everyone and welcome to a new discussion which we will be discussing about groundwater modeling. It is in two parts. So, let us start discussing about the first part. Before that I would like to mention basically what is a model. So, model is an abstract version of reality and no model can ever represent the natural world in any system, in computer or anything. But why we go for modeling? Because many times we want to analyze things in a manner so that we can predict things. So, models are also for prediction. What is going to happen to the availability of water for agriculture, for irrigation, for drinking and other things. And if it is related with the pollution, then how it is happening. So, flow models will play very important role. So, that is why modeling it is done. Because one other important thing that these models require lot of inputs of data. In many cases we do not have those kind of detailed data. So, whatever the data is there, we feed to the models and we get some outputs which may be very useful. So, there is said that the model terms here refers to any representation of a real world or an abstract representation of reality, not exact real world, but an abstract a reduced version of real world. And we keep in the models the main influencing parameters. So, in a hydrogeological modeling process, it starts with identifying and defining problem and setting use of the modeling objectives. What are the objective of the modeling? So, like here what we are seeing that there is a evapotranspiration or a transpiration by vegetation, there is a water table and unsaturated zone is there, water table is here and a stream, unconfined aquifer conditions, confined aquifer conditions. So, we see that this is a very simple, starting with a very simple approach about the model. So, what we are seeing, the direction of groundwater flow, very low hydraulic conductivity bedrock which is at the bottom as mentioned bedrock, low hydraulically conductivity confining unit which is creating and this bedrock and that low low permeability zone is creating confined aquifer and top of which you are having a high hydraulic conductivity aquifer which is an unconfined aquifer. So, it is a simplified version and that is what we start here. So, why we need a model? As also mentioned here that to understand why a flow system is behaving in a particular manner. So, we need to know so that we can predict what is going to happen in future. If water table is goes down, if water is withdrawn and so on, or some pollutants are entering into the system, what is going to happen. And also to predict, this is what I was mentioning, the purpose of all modeling is to predict, to create future scenarios before anything really happens. So, predict how a flow system will behave in future and to analyze hypothetically flow situations in order to gain generic understanding of that type of flow system, to develop better understanding of an subsurface regime. If we are talking here is the groundwater modeling. So, that is why I have used word subsurface understanding and we would like to know how water will flow and other things also. So, there are two major technical reasons why we need modeling. The first one is natural systems, that is hydrologic, hydraulic, groundwater etc. Natural system means here are very complex and highly dynamic in nature and therefore, it is not easy to understand them without bringing model and model is a simplified version. So, we basically the complex system through models we try to make it simple so that we can understand the entire system. But our current knowledge about these systems is still limited about hydrological. So, and that if we have got a model for certain area for certain purposes, that does not mean that this is the real, it is representing the real situation or real scenarios, future scenario, not at all. Because our knowledge about the these systems, hydrologic, hydraulic and groundwater are quite limited still. So, there are limitations all around of current measurement techniques, limited availability of spatially and temporally distributed hydrologic, climatologic, geologic, pedologic and land use land cover data. All models are data hungry, and more the data or more the information about surface or subsurface conditions we are happening, better our models will perform and we would be able to predict in a much better. But how to bring that data? Because we are having limitations of current measurements. We are not having exhaustive measurements of every parameters which are influencing our groundwater regime. So, since we are unable to measure everything, we would like to know about a hydrologic system. We need a means to exploitation from whatever the measurements are available. And in beginning when I started discussion on that, I said that in most of the modeling when you start working, all types of data which it will ask, because developers might have included that requirement of the data. But if you are not there and that kind of data is not there, then you start assuming putting some data and getting some results. So, these when data is not available both in space and time, especially also with the time also, particularly to ungauged catchments, because every catchment like in this country is not being gauged or means what is happening to the discharge in every catchment. So, in such cases data will not be available, and into the future where the measurement is not possible, in order to assess the impacts of future hydrological changes. And for that purpose, the aim of this groundwater modeling is that whatever the data is available we can model. Suppose in the surroundings we are having some discharge information. So, we try to model for that watershed or that basin for which we do not have direct data, and to some extent that gives a quite good information also. So, models provide a means of quantitative extrapolation or prediction, which is finally helpful in decision making. When there is no information is available, less information, limited information is available, then the output from models are really helpful to make the decisions at that moment. Because otherwise how can you wait longer if the requirements is there, how can you wait longer to collect more data and so on. And some of the data cannot be collected because some models will require data of recent past as well. So, we see that how broadly the models can be used. So, there are predictive tools. Models are focusing on the predictive tools when the objective of groundwater modeling is to predict the impact of proposed action on existing hydrologic or hydrogeologic conditions. If reservoir is coming, what the impact it is going to have. A big colony or industry is coming, what is going to happen to our groundwater regime, as if water is a lot of water is exploited or withdrawn from our aquifers. So, predictive tools are there, and then interpretive tools, models are used to interpret or research tools when the objective of modeling is to study system dynamics and understand flow and transport processes, how water will flow and other things which might there. So, this is interpretive tools. So, thus the interpretive modeling helps gain insight into controlling parameters, and this is going to be a site specific to help assemble and organize field data and formulate ideas about the system dynamics. Because we know that overall the groundwater is a system and is a dynamic system, and when we think from the interaction of surface water and groundwater, it becomes more challenging, or this systems really becomes more dynamic in that sense. So, further third one is the generic tool models which can also be used to study processes, for example, flow or transport processes of groundwater in a hypothetical hydrologic or hydrogeologic system, which are called generic applications. So, these generic models are used to develop management standards and guidelines for a given region or an area as a screening tool. So, for preliminary assessments, that is why screening tool to identify regions suitable for unsuitable for some proposed action. So, as I have mentioned that if some new surface water body is going to come or over exploitation of water because of industry other thing, then what is going to happen. So, that one would like to know before a license is given to such activities. So, note that the predictive modeling essentially requires calibration, and for calibration again you need the data, whereas the interpreted modeling and generic modeling do not require necessary calibrations. So, in that way these can be much flexible than predictive modeling, but the ultimate aim is of on any kind of modeling in this domain is for prediction. So, these are the hydrologic models, the material models are there, mathematical models are there, in which you are having empirical models, you are having theoretical models. In material models you are having physical models, and of course, the analog models are also there. So, this brings the classification of hydrologic or hydrogeologic models. So, if we see that in empirical models, these are also called the black box models, which uses the regression and ANN, that is artificial neural network based models, very popular nowadays, and then theoretical models, which is the water balance models, analytical models and numerical models, and those are again useful, which are mathematical based. Analog models and physical models are not of that, they are not in that great use. Further, this mathematical models can further be classified. One is based on the simulation models, another one is the optimization models. So, simulation models include the empirical models, and then also analytical models, numerical models and hybrid models. These two are becoming popular. Optimization models with constraints, optimization models without constraints. So, that kind of classification can also be done. So, first we will discuss very briefly what is the material models. Material models can be either physical models or analog models, and a physical models is a tangible construction representation of a portion of natural world, and for example, a scaled down version of real system. That is what is model is, real abstract version of reality, and these are a miniature scaled version of particular watershed or channel. Physical models have been important means to understand the problems of hydraulics and fluid mechanics, whereas material models on the which are analog models, analog models under this material models category use substances other than but analogous to those in the real world. So, they are again may not be directly linked here, because other substances, we are not talking about other substances in groundwater, we are talking only water here. So, these analog models use the observation of one process to simulate a physically analogous natural processes. An example of analog model is like electric analog model, which is flow of electricity represents the flow of water. So, here this is what the other than water. So, material models are there, but whatever the understanding we develop here in electrical world or electricity flow can also be understood in water flow, or vice versa is also happening, because the flow might be, the concept wise might be same. But anyway, in past variety of analog models have been used successfully in simulating groundwater flow under various boundary conditions. So, these have also been used, but now we are having better models which are based on mathematics. So, we call as mathematical model, and which are based on mathematical expressions and logical statements combined in order to simulate a natural system. So, this is all about a simulation of a natural system. You can't create the natural system, you cannot represent the natural system through a model. So, you try to simulate a natural system, and this mathematical model uses a governing equation thought to be represent the physical processes that occur in the system, together with equations that describe heads or flow flows along the model boundaries. So, boundary conditions are there also. Now, mathematical models are for time dependent problems. Equation describing the initial distribution of heads in system is also required, and that is called initial conditions. So, you are having boundary conditions, you are also having initial conditions. So, you start with initial conditions, also boundary conditions are there, and try to predict something. So, mathematical models range from single linear regression equations to the highly complex partial differential equations, and they can become, but again there will be some limitations also of different kinds of mathematical models. So, these models, the mathematical models, can solve analytically using calculus or possible for a limited number of cases, which are known as analytical models, or they can be solved numerically using numerical techniques possible for simple as well as for complex cases, which are known as numerical models. So, they are becoming more popular in that case. Now, analytical models may or may not involve a computer, but the use of computer is necessary for solving numerical models. So, computers are available, all kinds of computers are available, that is why numerical models are more popular. Mathematical models can be solved using a set of commands on a computer is through a computer program. Now, mathematical models can also be classified, as we have seen while classifying these models, as empirical model or theoretical models. So, empirical models are based on input output relationship and do not necessarily simulate the actual processes involved. So, therefore, they will have limitations. Such models rely on observed input and output data and simply relate to the output to a given set of inputs through a structure which may be fully statistical or partially mathematical. And therefore, the empirical models are also known as black box models, and they do not help in physical understanding of the process involved, like regression models or artificial neural network based models, ANN models. Now, when we go for development of a groundwater model, what are the phases, what are the stages? So, the first is the mathematical model, which incorporates the description of key processes that determine a system's behavior with varying degree of sophistication. Sophistication means here that how best you can create an output which should match with the real thing. And sophistication also means that how many parameters which influence our groundwater system can be incorporated in this. Then your model becomes really sophisticated. Phases of numerical groundwater model developments are, first of all, compiling and analyzing field data, and that is all the time for all the places not easily available, and very limited data is available, but anyway whatever is available. Further understanding of natural groundwater system, that for any kind of modeling that condition is always there. Further conceptualizing the groundwater system, selecting a suitable numerical model or code, and then calibrating. Calibration is very much required, and verifying, validating the numerical model. So, whatever you have predicted, whatever you have created or said, whatever the output, how to validate, how to say that this model works very well. So, validation of any kind of output has to be there, and predicting or simulating future scenarios, that is the ultimate aim of any kind of modeling is. And then finally, you present the results through all this modeling and their analysis also. So, with this I thank you all, and I will go for we will also discuss in the next discussion the second part of this modeling. So, thank you very much.